Hi, Algebra 2 honors. This is Unit 14, Days 8/9. So I'll actually break this up into two different videos for you. But we're on page 35 in the packet, and page 35 and page 36 are all going to be about applications that can be modeled using either sine or cosine functions. And there'll be a lot of things that I think you're pretty familiar with. But the first example to get started right away is an application involving a Ferris wheel. So let's read through this, and we're going to try and come up with an equation. It says for the distance of the rider from the ground as a function of time t in minutes. And we're going to start them in some different locations. But let's actually read what we have here. So a Ferris wheel is 100 feet in diameter and makes one complete revolution in 2 minutes. So there's a couple things that are labeled here. We see that if the diameter is 100 feet, that the radius would be 50 feet there. And the revolution that's completed in 2 minutes, that will be an important piece of information. We'll talk about that in a second. At the bottom of the wheel where the rider gets on, so the person's getting on right here, the seats are 4 feet above the ground. So this distance right here is a distance of 4 feet. So therefore, it makes sense that this label over here would be 4 plus the radius of 50, that if somebody's right here, and I don't know if you can tell, but there's actually a person sitting there, that would be a height of 54 feet. Okay. So we want to write an equation for the distance that the rider is from the ground as a function of time as this ride goes on for one cycle. We'll go around once in 2 minutes. So we want to do this in two different ways. Once where the rider starts at the 3 o'clock position, that's this part right here. And then we'll set up a different equation when the rider is at the bottom of the Ferris wheel. And we'll see what function makes the most sense. Okay. Let's see if we can graph this here. So if we think about our rider who's starting at the 3 o'clock position, they're starting at a height above the ground of 54 feet. Okay. And they eventually, as they go around, they're going to rotate this way and go up another 50 feet from there. So when they're at this point on the ride, they're now at a max height of 104 feet. Okay. So the rider starts there, they go up there. Then when they get here, they're back to 54 feet. Then they come all the way down to this part where they would have gotten on the ride, and that's at a height of 4 feet. And then back where they started, they made one complete revolution, so they're back at 54 feet, and that took 2 minutes. So we're going to label the x-axis as time and the y-axis as feet, and I think once I start connecting these points, you're going to see, oh yeah, I know exactly how I'm going to define this function. So we started at this height, we went up, we came down, we went even further down, back to where we started the ride, and then back up to our original location at that 3 o'clock position. So in terms of writing the equation, first and foremost, I hope that you're going to pick this out as a sine function. Okay, so this looks what we call sinusoidal. Okay, it's a fancy name just for saying that this can be modeled using a sine function. So some things that would be important to write for our sine function are, what's the amplitude? The amplitude is the height above the wrap line. Okay, so we have to be a little bit careful with amplitude. There's two different ways to determine it, but if you think about where that wrap line is, that the sine curve is wrapping around, what's the height above it right here? And we go 50 feet above, and at this point, 50 feet below. So the amplitude is 50. Winds up being the radius of the Ferris wheel there. Okay. Now, this idea of 2 minutes, that's how long it took to complete one cycle, right? To get from where I started back to where I finished. So that winds up being the period. The period of this is 2. Well, when we go to write the equation, we know that we need to convert, I guess, the period in terms of a frequency, because that's the coefficient that goes next to x, or in this case, t. So this is how we're going to do this. If period in general is 2 pi divided by b in the equation, let's set that equal to 2. And then from there, if you multiply both sides by b, we know that b is going to equal pi. So it's a little bit different. Usually the period is in terms of pi and the frequency is a whole number like 2. But here the frequency is pi, which gives you that period of 2 minutes. So right now we know the amplitude, which is the value of a. We know the value of b. Is there anything else we have to account for to get the correct equation of the graph? Is there just a vertical stretch and then a change in frequency? And the answer is, well, we haven't really accounted for this part, have we? There's that vertical shift that took the sine curve and moved it up 54 units to where that wrap line is. So the vertical shift of the graph is that we moved up 54. And as soon as I have all of those pieces, I think now good. There's no phase shift here, right? We didn't take the sine graph and shift it to the left or shift it to the right. But my answer to part A as a sine equation is going to be the following. I'm going to write in kind of a fancy notation. I'm going to say h of t equals, instead of saying y equals, I just like the function notation here. It's the height as a function of time. It's going to be 50 sine. Now what comes next is, usually there's an x in here, but I'm going to put a t for time. We have to put the frequency next to t. 50 sine pi t. And then at the end, let's put a plus 54. So that would account for the vertical shift. That should model exactly what we sketched over here. And if you're like, gosh, I'm really not sure if all those pieces put together really does model this graph, well, here's the really good news. We can graph it on our calculator and double check. So here's what we've got. In your mode, you got to make sure you're in radian mode. So if you haven't played around too much with radian mode yet, make sure you're in radians, because that's how I calculated this value of pi, right? In order to get pi, I was thinking about the period in terms of 2 pi, which is the amount of radians that we use to complete one cycle. All right, let's go to y equals. We're going to type in the equation 50 sine of, in parentheses, let's do pi x, close parentheses, with a plus 54. So 50 sine pi x plus 54. And then the last thing I want you to do is fix the window. What are we doing for our x values? We're going from 0 minutes to 2 minutes. So we actually just have to go 0 to 2 for x min and x max. And for y min and y max, I think setting the y min of 0 is fine, but the highest point we realized was at 104. So maybe I'll just squeeze out to 105 there. That should be fine. That should produce a graph that looks, hopefully, if we did this correctly, identical to what we did there. And if I hit graph, here we are. Yeah, okay, so we went up, we got to the highest point of the Ferris wheel, came back down to where we hit the grounds, and then we got back to where our original location was. That is exactly what we predicted based on this graph over here. It takes a little while to get used to some of this modeling with sine and cosine curves, but we're going to get a little bit more practice right now in the next example, which says, well, what if the rider started at the bottom of the Ferris wheel? How would this equation change if we want to start at the bottom and not at the 3 o'clock position? So for part B, let's see if we can sketch a quick graph as to what that would look like. Okay, so for somebody who's starting at the bottom, they're starting at that height of 4 feet. And then from there, they're going to get to a quarter of a cycle through. They're going to be at that midpoint of 54 feet. So they're going to come up to 54. Then if I go halfway around, they'll be at the total height of 104. And then they're going to start coming back down. So they're going to go down to 54 and then eventually back to where they started. So this graph looks something like this. And again, that still took 2 minutes to complete, to get from where I started at the ground level back to where I began. Okay. So based on all of that, this isn't looking as sine-ish anymore to me, because this was screaming sine to me based on what I know about the sine parent function. This is looking more cos-ish. In fact, it's looking more negative cosine-ish. It's the upside down cosine curve. It still has a vertical shift of 54. Still got moved up 54 units. It still has an amplitude of 50. This height above the vertical shift is still 50. It still has a period of pi, because it still took 2 minutes to complete one cycle. So based on all of that, let's see if we can just make some minor adjustments to part A and write it in terms of a cosine curve. So for part B, I'm going to say h of t equals, remember it's a negative cosine curve, so let's do negative 50 cos of, still the same frequency of pi, and then put a plus 54 at the end. And of course, we can check this one by looking at the same exact domain So we still want 0 to 2. I still have my y value set from 0 to, I guess I chose 105 there. Let's change the function up to what we just determined to see if it matches this upside down cos graph that we want. So negative 50 cos of pi x plus 54 is the following. All right, perfect. That's exactly what we wanted to see. Okay, so we see one complete cycle graph by the time I get to 2, which is how long it takes to make one revolution on the Ferris wheel. Okay. So if you have any questions about this example, they'll be more similar to it. In fact, I think we're going on a roller coaster pretty soon. That might be in day 9. But here's a good quick sample of how we can use sine and cosine functions to model circular motion, right? That's exactly what's happening. We're going around on the outside of a circle, and we're going up and down and up and down if we model that as a height with respect to time. Okay, let's try one more example. Let's do this one. The population of deer in a certain park is estimated to fluctuate between a high of about 1,900 animals in the year t equals 0 and a low of 1,200 animals 4 years later. The population then increases again to 1,900 after another 4 years. What is the average number of deer in the park in any 8-year period? Write a sine or cosine model for the deer population p of t as a function of time in years. So here's what we've got. We've got time is still our x-axis, so we had time was the x-axis before, but now the y-axis is population of deer. And it seems like we're starting at t equals 0, which is right here. We're starting at its highest population of 1,900. And then if we keep reading, we know that 1,200 animals are there 4 years later. Excuse me. So when I put time equals 4 there, we got to bring this down to 1,200. And then if I go another 4 years after that, it does go back to that population when it was at its max of 1,900. So we see a graph that looks something like this. Okay. So that's, once I sketch that graph, it's going down to the lowest amount and then back up to the highest amount in a period of 8 years. That to me is looking very cosine-ish. Okay, and it's not even the upside down cosine model, right? This is right side up cos. So in terms of thinking about the key pieces to write our equation, I don't see any phase shift again, so that's good. But I do certainly have a change in amplitude. We have to figure out what the frequency is. And then we'll have to talk about vertical shift, all of those key pieces. Okay, let's talk about vertical shift first, because if I know what the vertical shift part of this is, that will help me get the amplitude. All right, so for the vertical shift, the midline in this example is midway in between the highest and lowest points. So to find that vertical shift piece, that wrap line, we have to figure out what's the average of 1,200 and 1,900. So let's just quickly add that up, right? 1,200 plus 1,900. And then divide that by 2. The wrap line is at 1,550. That's the vertical shift, 1,550. Which now that helps me determine the amplitude. The amplitude is the max height above the wrap line. So you got to be careful. The amplitude is not 1,900. It's 1,900 minus 1,550, which should be 350, right? So the amplitude is 350. And the last part about the frequency, to develop that, we're going to use the same logic that I used up here a minute ago. Remember that one cycle got completed by 2 minutes? Well, one cycle of this cosine graph gets completed by 8 years. So if the formula for the period is 2 pi over b, that's what we know. We know the period is 8. So we have to set this up to figure out what b is, which represents the frequency. So if 2 pi equals 8b, that tells me that b is 2 pi over 8, which would reduce to pi over 4. And that should be all the pieces that we need to put together. We have the amplitude, we have the frequency, we have the vertical shift. There was no phase shift. So putting all the pieces together, we now know the function for the population, p of t equals the amplitude, 350 times cos of Go ahead and now use the frequency pi over 4 times t. Close the parentheses and then add on that vertical shift. Okay. I'll challenge you to check this on the calculator, and we'll make sure that next time we're in class together, that if I check this on the calculator, it looks exactly like we see in our model over here. Okay, and that we have that max height in the correct location. Okay, think about how we're going to change the window adjustments based on typing in this equation. But hopefully you can do that and check it on the calculator. That's it for day 8, and we have 2 more questions on page 36 that we'll do for day 9. So we'll take 2 days to kind of go through some of these applications with circular motion and populations here. So a little bit more to come with sinusoidal modeling. Have a great rest of your day.